we're dealing with indeterminate forms and how to find limits of them, derivatives of them. So up until now, we've talked about indeterminate forms of 0 over 0 and infinity over infinity by using a method called L'Hopital's rule. Now we're going to look at indeterminate forms of infinity times 0 and infinity minus infinity. Here's a note for this next section. If you can convert these equations to the form 0 over 0, infinity, infinity, do so because it's much easier. Because we just do L'Hopital's rule top and bottom and then wait till it becomes non-zero. So for example 5. As x goes to infinity, in this equation, 0 goes to infinity, sine 1 over x. 1 over x goes to 0, so sine of 0 is 0. So this one has the form infinity times 0. So when that happens, what we want to try to do when you have an equation like this, what you want to try to do is convert this into infinity over infinity or 0 over 0, a rational expression. By substitution, we can rewrite this equation as a rational equation. Because right now, as I said, it's infinity times 0. So what substitution will we use? The only thing we could really look at is if we set some variable h to be 1 over x, a rational equation. Then we can rewrite this as the limit as x approaches infinity, x. What is x? If h equals 1 over x, then x is equal to 1 over h. So this x can be written as 1 over h. And sine 1 over x is h. Since we did that substitution, we changed 1 over x to h, we also have to change the bounds of our limit. Because it's no longer x, it's now h goes to infinity. Well, I said, where does h go to? As x goes to infinity in this equation, where does h go to? 0. Don't worry about it. So what we have here is the limit as h goes to 0, sine h over h. From the squeeze theorem, the limit as sine over h, sine h over h goes to 1 by the squeeze theorem. We did that in chapter 2. Again, by using what we've done already or algebraic manipulations, we can rewrite these things and solve our equations much faster. The second one, let's look at the limit as x goes to 0 from the right of radical x ln x. As x goes to 0 from the right, we have radical x, ln x. We have to see what kind of what form this is in. As x goes to 0, square root of 0 is 0. As x goes to 0, ln x goes to negative infinity. So we're of the form infinity times 0. Remember, ln looks like this. So as we get closer to 0, our function goes to negative infinity as we get closer to 0. Now, how do we put this into a rational form? We can rewrite algebraically. We can rewrite the first term as putting it on the denominator and dividing it. Because square root of x is equal to 1 over square root of x. Now we're of the form of a rational. So as x goes to 0, this top one goes to negative infinity. And the bottom one goes to, well, the bottom goes to 0, so it goes to infinity. So it goes to infinity over infinity. Because it's a limit function and it goes infinity over infinity, we can use L'Hopital's rule. The derivative of ln x is 1 over x. The derivative of, let's rewrite this bottom part, is 1 over radical x is the same thing as 1 over x to the power 1/2, which is x to the power negative 1/2. So the derivative of that one is negative 1/2 x to the power negative 3/2, which becomes negative 1 over 2 x to the power 3/2. So that's the derivative of the 1 over radical x. So that gives us negative 1 over 2 x to the 3/2. One over 0 is infinity, negative 1 over 0 is infinity, so we're still infinity over infinity. But let's rewrite this. What do we get? If we rewrite this algebraically, we have the top fraction, leave it alone. Take the bottom fraction and flip it and multiply. Because we have a fraction over a fraction, we can rewrite it this way. So we have 2x to the power 3/2 over x. This is x to the power 1, which is 2 over 2. So since we have exponents top, subtract the smaller from the larger, so it's 3/2 minus 2/2, which equals 1/2. So our equation, as x goes to 0, becomes -2x to the power 1/2, which is x goes to 0, -2 square root of x. As x goes to 0, this goes to 0, so the whole thing goes to 0. Again, knowing algebra is very important. The stronger your algebra skills, the easier it's going to be doing all this stuff. All right, let's look at example 6. Example 6 has find the limit as x approaches 0 of 1 over sine x minus 1 over x. As x goes to 0, it's 1 over 0, which is infinity. We're of the form infinity minus infinity, which is indeterminate. So we have to algebraically combine these. Because if we just plug in the x's, we have 1 over sine of 0. Here's a packet for the rest of the course. That's for the rest of the course. So it's 1 over 0 minus 1 over 0, which is infinity minus infinity. We can't use L'Hopital's rule because it's a quotient, it's a difference equation. So what we can do is combine these two. If we combine these two, we have to get an x over x and a sine x over sine x. So it becomes x minus sine x over x sine x. Now we can look at L'Hopital's rule. So if we put in 0, we have 0 minus sine of 0, 0 sine of 0. This is 0. So we're left at 0 over 0, which allows us, gives us the what we need to use L'Hopital's rule. So using L'Hopital's rule, take the derivative of the top. The derivative of x is 1. The derivative of sine is cosine. And on the bottom, we have a product. So we got to use the product rule. The product rule, since it's a plus, sine times 1 is sine x plus x times cosine. Well, we just took the derivative, so now let's check it out. At 0, we got 1 minus cosine of 0, sine of 0 plus 0 cosine of 0, which is 1 minus 1, 0 plus 0, Okay, we're still at 0 over 0. So we look at this equation again and do L'Hopital's rule again. L'Hopital's rule again. So on top, the derivative of 1 is 0. The derivative of cosine is negative sine. So we have a minus a negative sign. Derivative of sine is cosine. Now we have to take the product rule of this. F is x, g is cosine, so f prime is 1, g prime is negative sine. So inside here, it becomes cosine x plus negative sine, which makes it minus x sine x. So we have sine x over cosine x plus cosine x minus x sine x, which becomes sine x. Cosine plus cosine is 2 cosine minus x sine x. Putting 0 inside there, we got 0 sine of 0, 2 cosine of 0 minus 0 sine of 0. Sine of 0 is 0. 2 times cosine of 0 is 1. 0 times sine 0 is 0. So we have 0 over 2, which is 0. And that's our final answer. Again, you have to remember how to do your product rule, your quotient rule, your derivatives of all sorts. So that's how we use that. So those are the indeterminate forms of 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity. Those are the different types of indeterminate forms we've looked at so far. There are some more. There are different types. There are 3 more different types. These are called indeterminate powers. These would include 1 to the power infinity, 0 to the power 0, and infinity to the power 0. Whenever you have these types, you can solve them using logarithms of the function. Why would we use logarithm? What does a logarithm do? Logarithm is used to get the variable, which is an exponent, out of the exponent. So, in other words, an exponential equation looks like this. That's an exponential equation where you have your variable as the power. The logarithm, the conversion of logarithms, if we take the ln of both sides, the natural log of both sides, you can't have exponents, so this come in front. So to solve for x, we divide both sides by ln a. And that's how we solve for the x, which is an exponent in a function. So that's what we would use here. More so, the properties we use here, there is a property that says this. The log base a of a to the power x is x. What this tells us is if your logarithm has the same base as your function, then it equals whatever the exponent is. More so, what it really means is this x goes out in front, and ln of e, since ln is the same base as e, this becomes 1. So we have x equals x. Same thing here. The log exponent comes out in front. Log base a of a, that becomes 1. So we have x equals x. Now, to solve what we're doing here, we're taking the limits. So in ours, we take the limit as x approaches 0, and we take the ln of a function, it equals some limit. As long as f of x is not 0 or negative or 0, we can take the ln of it. So if that's true, then our limit of our function, let's make this a, because it could go to anything. The limit of our function f of x is equal to the limit as x approaches a of e ln f of x equals e to the power l. Before we go any further, let's make sure we understand what this is telling us. So we have a function. If we take the ln of the function, what we're really doing is take the ln of both sides. So if our function it equals this, how does it equal that? Another property of log says that the base, and if the base of the logarithm and the base of the function are the same, then it equals x. So a to the power log base a of x is just x. Or e of ln x, since e and ln are the same bases, it just becomes x. So with this, f of x is the same thing as e to the power ln of f of x. Since these cancel, we get the limit of that. But since we took the limit of this, and we know that the limit of f of x is equal to L, then this is going to be the same answer. Since we know from here the exponent, the limit of ln f of x is L. All right, let's take an example. Because our entire objective is we have to get to this point, and what we're finding from our limit of our equation will only find our exponent. So show that the limit as x approaches 0 from the right of 1 plus x to the power 1 over x is equal to e. What is the power of e? Yeah, so this is what we're looking for. We have to take the limit of this function, make it equal to 1. How do we do that? So we take the limit as x approaches 0 of the ln of our function. And that's what we did here first. The limit of our function, we get a limit. And then once we find this, then we apply this. So what that equals, with respect, remember, this is our f of x. So we have the limit as x approaches 0 from the right of ln 1 plus x to the power 1 over x. Because that's our function. All right, using the properties of logarithms, when you take the ln of something, you can't have an exponent. So the exponent comes out in front of the ln. So this exponent comes in front of the ln, so we have this. What makes this equation ln 1 plus x over x. Can we use L'Hopital's rule? Because when we put 0 in there, ln of 1 is 0 over 0. This is 0 over 0. So yes, we can apply L'Hopital's rule here. We'll take the limit as x approaches 0 from the right. What's the derivative of ln 1 plus x? 1 over 1 plus x. Again, whenever you're doing these homeworks or anything, make sure you have your formula chart, because obviously you're not memorizing these. So we have to make sure we have, we just said 0. It's nowhere near 0. And the bottom, the derivative of x is 1. So this becomes the limit as x approaches 0 from the right of 1 over 1 plus x. When x goes to 0, we got 1 over 1, which is 1. So now, where does this 1 go to? Now we use our equation. We have the limit of x going to 0 from the right of our function, 1 plus x to the power 1 over x, is equal to the limit as x approaches 0 from the right of our function. What we say up there, the limit as x approaches 0 from the right is actually e to the ln f of x. What is ln f of x? Ln f of x is what we just found. Remember, this is what we're doing. The limit of ln f of x, the limit of ln f of x is what we just found there. So we have e to the power 1, which is e. That's what the question asks us to find. Use L'Hopital's rule to prove that this is equal to e. So what we have to do, we have to take our function, take the ln of it, and then find the limit of that. Use L'Hopital's rule. Example 8. Find the limit as x approaches infinity of x to the power 1 over x. So what is our f of x in our equation? What's our f of x?
1 to the power 1.
This whole thing is f of x. So using this formula, this is going to be important in this area. Now we have to take the ln of f of x. We have to follow this sequence. So we have L'Hopital's rule. gives us. Okay, first off, we have the limit as x goes to infinity. We have to take the ln of f of x. So what does that mean? That's the limit as x approaches infinity of the ln of x 1 over x. The exponent goes in front of the ln, so that gives us the limit as x goes to infinity of 1 over x ln x, which is actually the limit as x approaches infinity of ln x over x. Here are the notes for the rest of the semester. So when we put infinity, ln of infinity is infinity, x is infinity, so we have infinity over infinity, so we can use L'Hopital's rule. So looking at the limit as x approaches infinity, the derivative of ln x is 1 over x. The derivative of x is 1. So this becomes 1 over x. As x goes to infinity, this one goes to 0. So remember, this is our exponent of e. Therefore, our limit of our function is the limit of x to the power 1 over x So now we take the e ln f of x. So we have the limit of e ln f of x, which becomes e as x goes to infinity. We have e to the power. This is that value. So we have e to the 0, which is 1. There's our final answer. Once you find this value here, your answer is simply take e to the power of this, and you're done. That's what this is telling us. No, we don't need those. All right, that's it for that section. Any questions about it?